Good morning everyone. Thank you for joining me for this video. I am Mr. Ish. We will be talking about graphing derivatives but in a non-technical manner, because you could literally take a graphing software, a graphing tool, and graph any function that you wanted. You know, if you have any given function, f of x, and you take its derivative, what we have determined is something which looks like that. In terms of terminology, you can present this as the derivative of that. It's called a derivative because it has been derived from this original function through some derivative procedure. You know, you can graph any derivative, whatever it might be. I'll just give this a appearance of f of x, then you should be able to graph whatever it might look like, and this is all hypothetical, the derivative of that. The ability to draw graphs of derivatives is important because it helps you interpret what the original function might have been, or if you're starting with a function, it helps you interpret what your derivative graph might look like. Taking this as a very easy example, and I know I always default to this, if f of x is equal to x squared, you know the graph of that is easily seen to be this. You know, if you do the derivative of this, you've gotten the derivative to be 2x, therefore then the graph must look something like this. A line going through the origin having relatively a steep slope. But these are easy functions, and you know you can easily graph them out, especially when you have the derivative available. You know 2x is a linear function, something which is derived from y equals x, except here you have a slope slightly being more steep because of the coefficient 2. But for these arbitrary types of functions, how do you know what the graph of its derivative will look like? And that is what we're going to look at in this video. That will be the crux of this, like how you can decipher using a very simple technique, a non-technical technique, a technique of approximating or estimating slopes of tangent lines, how you can take an original function and be able to graph its derivative. A rough approximation of what that graph might look like, but close enough to a true representation that you can actually provide a reasonable graphic depiction of that derivative. Very quickly, let's just get this part out of the way as to why we are even bothering learning how to graph a derivative when you're given a function. Like, what is the purpose of this whole entire video, or the purpose of learning the technique which will enable us to do what I'm saying it will enable us to do? It's because of this. If you are given a function, you know normally you would do its derivative and you would get to its derivative of that function. There could be some instances where you're given a function which is amorphous or obscure in nature, it's very just difficult, and for whatever reason you couldn't carry out this procedure and arrive at a derivative factor. You just couldn't come to it. But however, you know what the function looks like using the technique that I'm going to teach you in this video. An easy technique. You should not feel that this is intimidating by any means, because it's easy. It's based on a lot of reasonable approximations, and it's easy technique. Based on this technique, you can come up at a good graph of the derivative. And you know, a graph of any function or graph of any derivative very well describes what the derivative or the function is or was. If you could come up with a graph of a derivative but you don't actually have the actual derivative, you can use and analyze the graph of that derivative and then start describing what the derivative could have been. Very quickly, and just as a very rough example, if you were given an obscure function which looks something like this. Something like this. We don't have to be 100% accurate, but this is a graph of our function, and you just could not calculate the clear derivative of it, but you can use a technique that you learn and you can come up with this depiction of the derivative. And now you have this depiction of this derivative, you can analyze it such that you can describe what the derivative would have been. For instance, some of your points that you can use to analyze this graph of the derivative would be from an interval of, let's say, minus infinity, right, and minus infinity to this point A, whatever this point might be A, the function derivative is increasing. See, it's increasing. Then from an interval, well, that's one point, from an interval of A to, let's say, B, from interval of A to B, your function derivative decreasing, right? It decreases. As you can see, there's like a little bit of a negative slope over here, it decreases. And then from an interval of B up to infinity, the derivative is constant. Another clear defining characteristic you can obtain just from the graph of this derivative, and you don't have this for whatever reason, but you have this graph of the derivative. Another point you can say is that the derivative happens to cross or intersect the origin. It crosses at the origin, and clearly does. It has a domain. Your derivative has a domain, let's say a domain of minus infinity to infinity. You can say it has a certain range. It has a certain range of minus infinity, right, up to perhaps this point right here, which could be C. It has that range. So once you're able to start describing your graph of the derivative and you accumulate this information and you collect it, then you can start describing what this factor would have been or what it was, even though you couldn't arrive at it. But let alone, if not even for this purpose, the purpose of being able to decipher a graph of a function, and from that graph and using reasonable approximations and the technique you will learn and come up with the graph of the derivative, that alone should be incentive enough for us to learn it, because it has a certain value to it. So before we start learning the technique for graphing derivatives, there's one very quick concept that we have to revise, and you know I've presented this because I presented as one of my earlier videos when we were talking about derivatives, and that was the video if a given function is differentiable or not. If you have an interval a comma b and this function extends over this interval a comma b, if you can determine a derivative of that function at any point from a to b, then you know very well that the derivative exists because that function is continuous. It might be sparking some memory in all of us that I'm talking about this, and I presented a good theory in that video. A function is continuous so long as it is differentiable at that point or at any point on that interval. If you can do a determination of its derivative, then that function is continuous. At any point where you can do a determination of a derivative of a function over an interval, it must be continuous. But then the opposite of that statement is not necessarily true, that just because a function is continuous, it does not mean that it is differentiable or that you can determine a derivative at all points on that function over that interval. Because there were 3 instances I presented in that video where you may have a function that may not be necessarily differentiable, 2 of which are in the condition where a function is still continuous but you still could not determine a derivative, and those were because of vertical tangent lines. You'll remember all of this, vertical tangent lines, and you had some sort of a corner or a kink in that function that it was continuous, but the presence of a corner or a kink or near vertical tangent lines prevented the ability to determine derivative. And the third condition, which if you have a discontinuous function or an interval that has a break in it, then you cannot do a determination of a derivative. You must remember these points as we go into this graphing video, because here's an example of a situation where you can have vertical tangent lines. You see right over here, from this point to this point right here, you have a near vertical tangent line which you can develop. A tangent line is a point which grazes your function at a specific point. If you try to draw a tangent line anywhere between this point to this point, you'll end up having a vertical tangent line, and you know vertical lines have no slope. Corners and kinks, what do they look like? Something which looks like this. At this point, both of these instances are functions which are continuous throughout. There's no break in it. But the corner and the kink and this near vertical aspect of this function prevents our ability to determine derivative at these points. And then you know what a break or a discontinuity looks like. A function which looks something like this, and here at this point or here of this break, you cannot determine a derivative. 2 of these are conditions where your function is purely continuous. There's no break in it, but you cannot determine a derivative. Here you cannot determine a derivative simply because of the discontinuity in that function. So you must remember this as we get into this topic of graphing derivatives. To learn the technique by which, when you start with a function, you have to somehow in a reasonable manner estimate what the graph of its derivative will look like, we'll look at 3 known examples. And then after these 3 examples, we'll switch over to those type of examples which are more obscure or amorphous in nature. Something which will be slightly more out of the ordinary. Those type of functions, they'll not have a given equation, we'll just be calling them f of x, and then we'll have to use those obscure functions to generate a derivative graph. But let's start with these 3 known examples first. the first of which is f of x is equal to a. You know very much easily that this right here represents a constant. So we're looking at equation forms over here, which would have been like y equals 2 or y equals minus 1, like horizontal lines. You know, if f of x represents a horizontal line and you were to do the derivative of something like this, you're doing a derivative of a constant, you know the derivative of this would equal to 0. But we're laying here in this video the framework by which you can, in a reasonable manner, depict a close to accurate representation of the derivative graph from a function. The first step you want to do is graph what you have. Y equals a, f of x equals a represents an equation which looks something like this, a graph of f of x equals a, and this intercept over here can be 0 comma a. You know it's a horizontal line. What you want to do in the procedures for this video, and the procedures that I would wish you would adopt, would be to come up with a good table of values, and the table of values would come something like this. You'd start with an x value over here, and we'll be repeating the same technique through the remainder of the examples, because that way they'll become concrete in our head. And then you'd be basically putting another column over here which would represent the estimated slope of a tangent line if you were to draw at your function at a given point. And you know, as I start doing this, it'll come clear as to what I'm doing. I have a table of values which will represent the axis values which I would have on this function f of x, right? And then I would, at each of these points which I will enumerate over here, we'll try to determine in a reasonable manner. It doesn't have to be accurate, but just has to be a good guess as to what the slope of a tangent line would have been at that specific point. And I would like to start from a left to a right direction. See, from a left to a right direction, going in here. And I think I would just pick an arbitrary point here, minus 2, minus 1, then my 0, then 1, and then 2. And I can put those right here, minus 2, minus 1, 0, 1, and 2. And at each of these x-axis values on my curve f of x, I'd want to determine what the slope of a tangent line would be if it were drawn to this. You know, for a horizontal line, a tangent line to it would be relatively easy to draw. At minus 2, you would draw a tangent to this curve, and it would just be right next to it, kind of a coincident line. And a tangent line over here would technically have a slope of 0, and the slope at that specific point would be a 0. Since this is a horizontal line, you can, at each of these points, generate a slope of a 0 for a tangent line at each of these points. Once you've developed this table of values, you have now a kind of a coordinate pair. You have 2 comma 0, 1 comma 0, 0 comma 0, minus 1 comma 0, minus 2 comma 0, where the x coordinate of that coordinate pair, which we kind of have in x, y, the x represents the values you've chosen from which you're determining at that specific point on your function the slope of a tangent line. The y values will represent these coordinates over here. Once you have these coordinates, you use these coordinates to generate a new graph, and that new graph tends to be the graph of your derivative to your original function, and you draw them exactly as you see it. At minus 2, I have a 0, so that's a minus 2 comma 0, and I'll put a dot over here. Minus 1 comma 0 right here, 0 comma 0, 1 comma 0, and 2 comma 0, and my derivative ends up being exactly what it is. The derivative ends up being the graph of a x-axis, which is really y is equal to 0, or you can say f of x is equal to 0. And it kind of confirms the idea that anytime you have a function which is a constant, you take its derivative, the derivative is 0, the graph of this 0 would essentially be y equals 0, or f of x equal to 0, which would be synonymous with your x-axis. So this right here kind of represents the procedure, but we have a known function over here. We know for any functions which are constants, their derivatives are always 0, and the graph would always be exactly what you see over here. We look at 2 other known examples, and we'll get into the more interesting examples. The preceding example, this one and the next one, these 3 which I am presenting, I'm only calling them known because I'm actually giving you what the function is. They're known to us. F of x is equal to x, or y is equal to x, and we know very clearly we can do a clear derivative. If you're looking at something which is y equals x and you do the derivative of this, you know exactly what your answer is. If the derivative is 1. We know exactly what the function is. There's no obscurity, and we know exactly what the derivative is, and we can easily draw that. Anyhow, y equals x looks something like this. Start with the table of values. You know you have a constant line over here in terms of its rate, its slope. It's a linear line. We'll start with the table of values. The x-axis values will represent what our chosen points are, and on those points on the curve we'll determine what will be the y value coordinates, which will be the slope of the tangent line at that specific point. I don't have to pick too many points here. I can again pick the same. -2, -1, 0, 1, 2. And you'll see the process is not hard. And when we get into the additional examples after these first three, you'll see with those obscure functions, again, the technique is easy, but it's interesting. At -2, if you were to look down on this curve and draw, because this right here is -2, here is 2. At -2, if you were to peep down over here and try to draw a tangent line, you'd end up having a tangent line, and then you would look at it in terms of the slope of this tangent line. You see there's a tangent line is going upwards with a relatively even steepness and flatness to it, and you could say the slope should be just a 1, a positive 1. It's a positive 1 because from left to right this tangent line points upwards, therefore has a positive slope. But since this is a linear line, it has a constant rate of change, the constant slope. At each of these points, -2, -1, 0, 1 and 2, the slope should always be upwards, positive 1, and that's exactly what we find. Now with these coordinate pairs, if you draw a graph and you just plot them out, 2, 1, 1, 1, 0, 1, -1, 1, -2, 1, and you'd end up having something which looks like this right here. And what is this line? It's y equals 1, exactly what you see over here. The derivative, let's not forget this little prime over here. The derivative of y equals x is just a 1, and in terms of graph it's f of x, f of prime x, or y equals 1, and that's the graph of this derivative. Again, it's known to us because we have a clear function. We know clearly what the derivative is, and our procedure is over here, and we can draw out the derivative graph. So as the last of our three known examples, we have y equals x squared, or f of x equals x squared. And in case you're wondering what's the point in even learning this whole video or watching this video, or why am I even showing you this technique? Well, the technique and the point to this video will become clear after I show you the examples from this point onward. After this example, the future functions which we'll show, then you'll understand why we're learning this skill. Because for these known functions, it's easy to generate a graph of the original function and the graph of the derivative. When you have an unknown function or a function which has a certain level of difficulty to it, and then being able to reasonably estimate what the graph of the derivative is, that's where it counts that you know how to do this technique. And you'll see it from the examples after this one onwards why it's an important skill to learn. F of x equals x squared is easy, parabolic curve pointing upwards. If you do the derivative of this, it's easily 2x. The graph of the derivative should represent a linear line with a relatively steep slope. But you should be using the technique that we're talking about here. Generate a table of values with the x values, which will be the points that you'll pick out, and then those points on the curve, you'll determine what the slope of the tangent line would be like at those specific points. Let's go again with -2, -1, 0, 1, and 2. And then we'll generate what the possibilities are for tangent line slopes to be at that specific point. At -2, you end up somewhere here on the curve and you draw a tangent line. You end up having a tangent line which is going downwards from left to right. See, as you go from left to right, your tangent line goes downwards, and it goes down with a relatively steep character to it. So I'm just going to say it has a minus, but it'll be a steep slope. We don't even have to quantify. We can just say it's minus and it's steep. When you look at -1, you look over here and you draw a tangent line. You relatively again have a minus slope, and a tangent line with a minus slope because it is going downwards from left to right, but it's not as steep. And we can just give it like a character of minus, and let's just say less steep. Alright, it's steep, but it's less steep. Less steep definitely than -2. At 0, if you draw a tangent line, you have a tangent line which goes across, and this tangent line is a horizontal line. It ends up having a slope of a 0. At 1, because this is like an even function in terms of the right side and the left side, it's a mirror image, you can copy the exact same quantifying or qualifying values except change the sign, because at 1 you'll have a relatively less steep tangent line slope, except it's upwards, therefore it's a positive, but we'll say less steep. At 2, you'll have a steep tangent line, but it's upwards, therefore we'll say positive, and we'll say it's steep. Now with these values you have over here, x and y values, you can draw a graph of your derivative, which we know is really 2x, and you can quantify these values over here in some regard, because all of these over here represent some sort of a y value. 0, 0, we can just do that. 1 and less steep, well, we can just do something like this. At point 2 we have a pretty steep, at -1 we had a less steep, at -2 we had a pretty steep, and then we just connect the dots to a good value. With a human hand you're prone to making errors, but you have a line over here which is definitely not flat, but it's slightly having a steep character, something which would mimic or mirror the type of graph you'd see with 2x. So if supposedly we never knew the derivative template techniques, and we don't know that the derivative of x squared is a 2x, we suppose we just didn't know that the derivative of x squared is a 2x because we don't know the power rule, we could use this technique over here and come up with this value and be able to graph the derivative graph, and we could end up saying reasonably that the derivative of x squared is a linear line which happens to be at a minimum relatively steep, and it goes to the origin. See that at that minimum level of information we do have some usefulness there, because we're starting out here with a function that's parabolic, but we can say without knowing the derivative procedures at all that the derivative of this using these estimating procedures and the slopes of the tangent lines at the specific points, that the derivative of x squared would be a linear line having relatively steep character. So at a minimum you can say that, and being able to say that without being able to calculate a derivative has a certain value to it. Now in the remaining examples of this video, see in your mind, you can ask yourself that you're given an amorphous function, and you can now, after learning the procedures and techniques of this video, how you can come up with a derivative graph, and from that derivative you can start verbalizing several characteristics. I won't verbalize those characteristics as we do each of those examples, because you can do that in your head. Our goal is only here to learn this graphic estimating technique using chosen x values and reasonable estimates of the tangent line slopes at each of those, and then you generate a graph of the derivative. In the remainder of this video, we're not going to be looking at the normal functions we're used to, like x squared or root x or sine x or whatever. We'll be looking at some of these obscure graphs, obscure functions, because we have to be able to decipher what a graph of a derivative would be for any function that's presented, and we don't even need to identify the function having a specific equation. We just are trying to determine what the graph of the derivative might look like for the given function at hand, and we will learn the procedure that I would like you to follow for how you would go about doing that. And you would always look at everything in terms of your graph from a left to right direction, and then you would start by labeling some points. We can start by labeling a point here, -3, this can be a -2, this can be a -1, here can be my 0, that would be 1, that point here 2, and then that point 3. At each of these points we would then start identifying or guessing what a reasonable estimate of the slope of the tangent line might be. And I'll write slope of the tangent right over here. And we will start in a left to right manner, and we will try to be reasonable. And this is going to be starting from right over here, from a left to a right direction. When I'm looking at -3 and I were to draw a tangent line over here on my curve, assuming this curve is going towards infinity, a tangent line would be pretty steep. You see, it would be pretty steep. And you know, when lines are going downwards from left to right, they have a negative slope. When a line is going upwards from left to right, it has a positive slope. So at a -3 on your function, if you were to draw a tangent line, it would be pretty steep. It would be a very steep tangent line. At -2, you could still draw a relatively steep tangent line. Remember, I'm drawing with the human hand, so it will be a little inaccurate in terms of drawing, but you can get the idea. It would be still a minus slope because the tangent line would be pointing downwards, but it would probably be less steep in terms of the slope. At a -1, at this point right here, if you draw the tangent line, it's a horizontal line which would have a slope of a tangent line of 0. At a point of 0, if you were to draw a tangent line, it would be an upward facing line, but you could say it would relatively have a slope of a 1. Reasonably steep, reasonably flat, we'll just call it a slope of a positive 1. At a point of 1 on your graph, you end up having a horizontal line, it would have a slope of a 0. At a point of 2, you'd have a tangent line which would be pointing downwards. It would again have a negative slope, but you would say it would be minus, but perhaps less steep. At a point of 3, you could have a fairly steep, and we'll just say a minus steep slope. All you have now are these points which you can graph in terms of your derivative of the graph, you just plot this out, and you can plot this out in any order. At point of 0, I have a value of 1. At point of 1, I have a value of a 0. At point of minus 1, I have a value of a 0. At point of minus 2, I kind of have a minus less steep slope, so I can give it like a minus, like a relatively good y value. At a minus 3, I can give it even a more steep or a lower y value. At a point of 2, I'm having a minus, kind of a bit of a symmetry going on here. At a point of 3, I'm having a relatively steep minus, and steep minus value for the y. And when you connect these out, you end up having a graph which turns out to look something like that. And then you can say this right here would represent a good estimate or a good graph of what the derivative of this function would look like in upside down parabola. And I would be fairly confident to say that this graph of the derivative of this function is good. So let's continue on with this endeavor to learn how we can graph derivatives of arbitrary functions given the graph of the original function, and using this estimate procedure, which involves you identifying x-axis values and then getting a reasonable estimate of what the slope of the tangent line would be on your function at that given point. And we could start by identifying values, and we could say this right here is a minus 5. We could come up here with a minus 1, right here at a 0, and then a 1, and you should try to be symmetric with your chosen points. At a minus 5, if you're looking at your function over here and you're to draw a tangent line, it would probably be relatively flat. I would just say call it flat, and I just put 0. Likewise here at 5, you can also call it 0. Remember, it's just estimating. We're not being overly accurate over here. At a minus 1, if you were to draw a tangent line, it's a downward facing line but relatively steep. You can just say at minus 1 you have a minus steep slope. At 1, when you draw a tangent line, you're having an upward facing line. Perhaps using the word steep over here is not too good, because you could say it's minus but it's less steep, because it doesn't look too steep to me. You have to have some sort of good judgment over here too. At 1, you have a relatively positive because it's pointing upwards from left to right. Remember, you're looking at everything from left to right, but positive but less steep. Again, this is not hard science over here. It requires just a good level of judgment, and pretty much that's about it. At 0, if you were to draw a tangent line at this point, it would be a flat, and you'd call it 0. Perhaps here at the area of minus 5 and 5, I shouldn't be calling it a 0, because you can have a little bit of an inclination over here. I would say at positive 5, it would be a very shallow slope. A shallow slope. It's still pointing upwards, but positive shallow. Here it's going to be minus but shallow. Now let's graph these out. The graph of the function's derivative would look as you see before you. Start with the easiest point, 0, 0, right here. Then start with 1. 1 is a relatively small positive. You can call these as like positive y values, whether they're large positive or small positive, or they can be minus y values, large minus or small minus. And then minus 1, we have a relatively less steep, but it was still coming down here in the minus zone. See, minus 1, you have a minus less steep, so we'll call it a minus y. At positive 5, we have a relatively shallow, but still a positive y value, because these some way, shape or form are indicative of what you'll place in terms of your y-axis. At a minus 5, you have a relatively shallow and a smaller y value, and it seems like the derivative graph looks something like this. And you can see on the software, if you were to have the equation of this and you to do the derivative of that, your graph should look like this, and I'm confident we have a good result over here. Okay, let's look at this function over here. I'm hoping that this topic is proving to be relatively interesting, because it's more of an estimation and an exercise of reasonableness than anything else. Let's come up with some arbitrary points. I can have this point right here and I can just say minus 2. I can have this point here and call it a minus 1. This point here will be 0. This point right here will be 1. This point right here will be 2. I can have a point right over here, minus 3. which would represent something on the steep aspect of this line, and this can be 3 over here. And then let's come up with these minus 3, minus 2, minus 1, 0, 1, 2, 3. At a minus 3, I would end up very much so on this curve, and a tangent line, I'm not going to draw it, would be something which would be pointing upwards, but it would be very steep. So at a minus 3, on this curve, I'd have a positive but steep, very steep. At a minus 2, which is representing this point right over here, I'm right on this curve right over here, and again I'm having a relatively steep, and it's pointing upwards, so it's a positive steep. Minus 3 would have been very steep. Let's give it that little extra characteristic of it being very steep. At a minus 1, if I were to draw a tangent line, it looks relatively flat, and it's 0. At 0, I draw a tangent line, it comes out flat. Horizontal line, so it's 0. I could have probably picked a value right over here, like a minus half, because at a minus half, let's just add this other point right here. At a minus half, if I were to draw a tangent line, I'm getting a relatively, I would say a minus 1, a slope of a minus 1, because it's pointing downwards. Let's add this other point right over here for half. At an x-axis value of half, I would have an upward facing tangent line. You can probably see it as I'm drawing it, and I would give it a slope value of 1, positive 1, because it's pointing upwards. At a value here of 1, I would have a flat 0. At a value of 2, I'm having a downward steep line. Look, it's downward tangent line, and I would say it's minus steep. And likewise here at a value of 3, I would have a very steep, but it would be downwards, and we can give it very steep characteristic. Now we have a bunch of points over here we can use to graph what the function derivative would look like. And let's start graphing it out. And we can start from left to right. At minus 3, we have a very steep, but it's a positive. Let's do minus 1, minus 2, minus 3, 1, 2, and 3. We can put the halves in between. At minus 3, we're very up over here, because it's a positive steep, and these things here are indicative of what your y-axis values will be. At a minus 2, we are relatively steep. Let's just call it over here. At a minus 1, we were at a 0. See, minus 1 comma 0. At 0, we were at 0 comma 0. But let's not forget this. At minus half, we were at a minus 1. We'll bring a point right over here. At half, we were at a positive 1. We'll call it right over here. And then let's come over at 1, we were at 0 in terms of the slope of the tangent line at that specific point on your function. At 2, we were at a negative steep value, which is like a negative y value. At 3, we were at a minus, but a very large minus value. You connect the dots, and you end up having a function which looks something like this in terms of the derivative. And you can say that this would be a good reasonable approximation of the graph of your derivative for a function which looks something like that, and I'm confident it would look good. Now it gets a little more interesting, and I hope you're picking up now on the technique. Look, 2 specific points stand out very well over here. Actually, we'll say 3, 2 of which we have corners or kinks. So you know you cannot determine a derivative at these points. Even though your function is purely continuous, it is not 100% differentiable at all points over this domain. And another thing which points out that these are linear lines. So these linear lines will have a constant slope across that portion of linearity. So we'll have an interesting graph over here of the derivative of this function. And let's start out with arbitrary values. The tangent lines, the slopes of the tangent lines here represent our y-axis values. Alright, y-axis values. I want to look at this point right over here and just say it is minus 5. And look at this point right here and call it positive 5. I want to look at this point right over here, and we'll say that this is minus 2. Remember, this is just estimating here, and this point right here is a positive 2. This point right here is 0. But we won't write the 0 for space limitations, because I want to look at these points in between. I have a 1, I have a minus 1, I have a minus 3, and I'll have a positive, well, let's not even put a positive, and we'll have a 3. So we have all of these points to plot in terms of their tangent line. Let's come over here. Minus 5, minus 3, minus 2, minus 1, and then we have a 0, 1, 2, 3, 5. At a minus 5, if you were to look over here at a minus 5, we have a flat line, linear line, and the slope of the line here would be going upwards. we would just say, I would just call it a plus. It doesn't look too steep, it doesn't look too shallow, I'll just say 1. At minus 3, we're still on this same part and we still have the same slope. I would say plus 1 because it's an upward facing line from left to right. Remember, always look from left to right. From left to right, these tangent lines drawn over here would be upward, so they would have a positive slope. At minus 2 we hit this kink. When we hit a kink, we cannot do a derivative over there. If you cannot do a derivative over there, you cannot and ideally should not draw a tangent line. Therefore, there's no tangent line at a kink or a corner or at a discontinuity. At a minus 1, we end up somewhere right over here. If you were to draw a tangent line, it would be, let's say, a minus 1, because you'd have a downward facing line right on this tangent line to this existing curve. At 0, right here, you still are on this linear line from this point right here to this point right here. You're still on this linear line, and you would say it would still have a downward facing line, tangent line, and the slope would be a minus 1. At 1, you're still on the same curve with a slope of minus 1. At 2, you end up hitting this other kink, and we'll put a little x over here because you cannot do a derivative, therefore you cannot do a tangent line. At 3, we end up over here, but now we're looking at an upward facing tangent line. I'm not saying this is my upward facing tangent line, I'm saying a line drawn to this existing line would be upward facing tangent line, and I would give it a slope of plus 1, and likewise at 5 it would be a plus 1, and now we have our points. The derivative graph would look like this, and I'm going to start looking at this set of values over here. At a 0, I had a minus 1. Remember, these 1s and minus 1s are estimations only. We're looking at a general appearance of the graph only, of the derivative. At 0, we have a minus 1. At 1, we have a minus 1. At minus 1, we have a minus 1, and we have something which looks like this. And then at minus 2, we have a break. At minus 2, we have a break. So we'll put a little circle over here because there's a break. At positive 2, we have a break. At positive 2, we have a break. I'm going to connect these right over here. Then let's jump over here. We have to look at this part, and then we'll look at this part. At minus 3 and minus 5, at minus 3 and minus 5, we have a 1 and a 1. We have a 1 and a 1, and we'll connect it with this break we have over here, because this right here will represent, we have this upper lip corner, the kink. And let's erase it just so we're neat. Now let's look up over here. At 3, we have a positive 1. And at 5, we have a positive 1. Connect it and add it with this little break you have, because this break over here will represent this downward kink you had in your curve. Alright, and let's erase this for neatness sake. So this is what our function derivative graph looks like. You have this open break over here, and then you continue from here, then you have this, and then you go on over here. These breaks over here represent the areas of your kinks where a derivative could not be determined and where a tangent line did not exist. So that should look like a good graph of the derivative. This will prove to be a very interesting question, because what we have here is just an even function, a graph of an even function, but has a start point and has an end point. It doesn't go towards infinity. It actually has an ending and an originating point. And as we go through this one specific one, you'll find it to be quite interesting. We'll start with our table of values, x values, and then what will represent the y value will be your slope of your tangent line. Alright, the tangent line slope. And we should come up with good approximations over here. At this point over here, I can just, let's say, minus 5. Because it looks like an even function, you'll have symmetry of your coordinates. This would be a positive 5. I can come up with an arbitrary value, minus 3, a minus 1, a 1, and 3, and then of course the 0 in between. One thing which stands out over here is right here at the origination, we might end up having vertical tangent lines. I was talking about the differentiability of a function. If you have a corner or a kink, or you have a discontinuity, or if you have a vertical tangent line form, it can limit the ability to determine a derivative at that point, because vertical lines end up having a slope for vertical lines. See, VL vertical lines have a slope which is undefined, because you end up having a change in y and a 0 in the denominator comes up, because there's no change in x, it zeroes out. You cannot have a slope determination of a vertical line, and if you're drawing lines which are ending up to be vertical, then you have that same problem arise, and hence the vertical tangent lines even if a function is continuous, you have an area or a point where the derivative is not determined. So let's identify these points. Minus 5, minus 3, minus 1, 0. Remember right here is 0, 1, 3, 5. And because this is an even function, whatever points we determine here in terms of the slopes, we can just copy them over here because they'll be exactly the same, except for the signs. We'll have to adjust the signs, but the value of the slopes will be the same. At minus 5, I'm determining there's a tangent line forming a vertical tangent line, so I'm going to exit out, and likewise at 5 I'll exit out because I don't like the fact that we have a vertical tangent line, therefore we shouldn't be determining a slope of a tangent line over there. At minus 3 you would have a slope which would look like that, relatively, you can say it's a positive, it's of course it's a positive slope, but you can say it's relatively not too flat. I would say let's call it a plus 2. At minus 1 you have a relatively less steep of a tangent line, relatively more flat, but it's still in the positive because going from left to right the line angles upwards, and you always look at your determinations from a left to a right in terms of your coordinates and in terms of the assessment of the slope. At minus 1 I would say I would give it a plus 1. At 0 we have a tangent line which is flat, so therefore the slope must be 0. At 1 we have a line pointing downwards but relatively unflat, just same, having the same value of 1, but we'll call it a minus 1 because this line slopes downwards. At a minus 3 you have a line, tangent line which can be drawn downwards, and we'll, instead of saying plus 2 we'll say minus 2 because it points downwards. So we have the points we need over here to determine what a graph would look like. Now an interesting fact over here, because we had vertical tangent lines at 5 and a minus 5, we can just call this 5 and minus 5, minus 5 and 5 over here. We can draw a vertical asymptote. This right here is giving rise to a vertical asymptote, this right here is giving rise to a vertical asymptote. We just have these points in between now to plot. At 0 we had a 0. At a minus 1 we had a positive 1. See, at minus 1 you have a positive 1 value in terms of the y. At minus 3 you have a relatively large, heck I could have even given it a more steep of a value, but we'll keep it as is. At 1 we have a minus 1. See, at 1 we have a minus 1. At 3 we have a minus 2. At 3 we have a minus 2. So we end up having a graph which will come out like this. And that will be a good approximation of the derivative graph for this function over here. And I'm happy with this result. We'll look at 3 more examples in this video and then we'll wrap it. Remember, our goal is just to be able to look at a graph of a function and see and estimate to a reasonable degree what the graph of the derivative would look like, especially in those instances where we have graphs of these types of obscure functions. And you know now the procedure start with a table of values x, and you know the y value or the coordinate is represented by the estimated slope of the tangent line. Remember, we're not talking about secant lines but tangent lines, and you have to come up with a good number of values. We can come up here with like a minus 2, and it can represent a point somewhere on this. This right here can be a minus 1. This here is 0. We can come up with a value 1 over here, 2 over here, and we can even come up with 3 over here. When we're looking here at minus 2, we're ending up somewhere here on the steep part of this, and the tangent line looks something like this. So let's come up here, minus 2, minus 1, 0, 1, 2, 3. Heck, even if I put like a value 10 over here, we could come up with some determination, because this thing would continue like this and it would relatively flatten out. We can probably add that. At minus 2 I'm having a positive tangent line but very steep upwards from left to right, so I'll say positive but very steep slope of a tangent line. At minus 1 I'm still over here in a steep zone. I can say positive line because it's upwards, and we'll still say it's steep. At 0 we begin to flatten out, and we can just say at 0 we have a slope of a 0. At 1 you have a downward facing line, right? Downward facing line, relatively steep, minus, and we'll say or relatively steep, not too steep but relatively steep. At point 2 we start having these downward facing tangent lines, but they're not as steep. They're still minus, but they're minus slopes because the lines are pointing downwards, and I'll just give it like a minus 1. At 3 I'm still having a downward facing line. It's not steep by any means, I'll say minus half. And then let's come up with this other coordinate pair for 10. At a value of 10, I'm having relatively flat line, so I would give it a slope of a 0. We have a good number of points here to determine the graph of what a derivative would look like. And let's plot it out over here. At minus 2, I have a positive, very steep, so let's do minus 1, minus 2, 0, 1, 2, 3, and then we can break away for 10. Minus 2 is a very steep slope, very high y value. At minus 1, it's a relatively high value. At 0, we end up having a 0. At 1, we have a relatively steep minus value, right? Relatively steep minus value. I'll come up somewhere over here. At 2, we begin to flatten out a little bit. At 3, we end up flattening out some more in terms of the y values in the negative range. And at a value of 10, we can just come up over here. We're pretty much at 0, or it could be something very close to 0, and our derivative function would look something like this. And you can try to get a gist of it like this, and that's what it would look like. And I would be truly happy with this result too. Alright, let's look at this one over here. This will be our second last question for the video. We have two parts over here which are relatively, these are all linear lines, but these two parts are not very steep. But this part here, this upside down V, is relatively steep. You have presence here of three corners, one right here, so, and the third one here. So these are areas where a slope cannot be determined because it's not differentiable, even though there is a continuity over here. We can come up with some values. Let's call this minus 5. We can call this minus 4, minus 3, minus 2. We'll call this 0, 2, 3. Just be, because it's symmetric about your y-axis, just be symmetric with regards to your points. X-axis values, and now you should be comfortable with the procedures. The slope value here of your tangent line, which is going to represent the y coordinate of your coordinate pairs, always looking from left to right. If your tangent line is pointing upwards from left to right, it has a positive slope. If it's pointing downwards from left to right, it has a negative slope. Same rule applies for secant lines even, but we should be talking here about tangent lines. At a point of minus 5, if you were to draw a tangent line at this point over here, you would have a relatively downward facing tangent line. It would be a minus, and let's not forget our points here. Minus 5, minus 4, minus 3, minus 2, 0, 2, 3, 4, 5. We're kind of running over here. X-axis values. At minus 5, we have a relatively shallow but downwards, and I'll just give this a value of minus 1. At minus 4, we have the same line, therefore we should have the same slope because it's still going to point downwards. At minus 3, we have a non-differentiable corner, a kink in your curve, so we'll put an X over there. At minus 2, at this point right here, if you were to draw a tangent line, I won't draw it, it would be right parallel to your existing line, and it would be relatively more steep because this upside down V is more steep than these other linear lines. It'll be pointing upwards, therefore it'll be a positive slope. I'll give it a value of 2 because I know 2 is more steep than a 1, irregardless of what the sign is. At a point of 0, we have a kink. At this point of 2 right here, you have a downward facing tangent line, but it will still have a relatively steep slope because there's symmetry around this V aspect of this. I'll call it a minus 2. At 3, we have a kink. We won't give it a value. At 4, we end up right over here. At 5, we end up right over here. These should have same type of slopes as this over here, but they would be upward facing because this tangent lines would be upward facing. If these were minus 1s, we'll call this plus 1 and plus 1. Now we have the points we need to generate the graph of the derivative. All of these points will help us in determining that. And it should be relatively interesting because these areas of non-differentiability will be areas of discontinuity on your derivative graph. So, but let's continue here. We have a minus 5, minus 4, minus 3, minus 2, 0, 2, 3, 4, 5. At minus 5, minus 4, at minus 5, minus 4, we're here in minus 1. It's called, this is 1, 2, minus 1, minus 2. At 5, at minus 5, we have a minus 1. At minus 4, we have a minus 1. At minus 3, we have a break. Let's plot out those points we can. At minus 2, we have a positive 2. At minus 2, we have a positive 2 right over here. At 0, we have a break. At 2, we have a minus 2. At 3 we have a break. At 4 we have a positive 1. At 5 we have a positive 1. So you have a bunch of points over here you need to relay. At minus 3 we had this break. So let's bring this break over here. Here's my break. Minus 5, minus 1, minus 4, minus 1, and minus 3 break. Then minus 2 is a plus 2. Minus 2 is a plus 2. 0 is a break. Alright, we can put a break over here. Let's try to be a little neat over here. Alright, and then 0 we have a break. At 2 we have a minus 2 right here. We're jumping back here. And at 3 we have a break. It comes here to the break. See, 3 we have a break. And then at 4 we have a positive 1. And 5 we have a positive 1. It's coming over here and it's going to break right over here with 3. We have a minus 5, comma, minus 1, minus 4, comma, minus 1 coming up to this minus 3, comma, break. Alright? Then we have a minus 2, comma, 2, minus 2, comma, 2, and this should extend all the way up to where the potential 3 would have come up to. So you could draw a straight line over here and then bring it all the way over here. Minus 2, comma, 2, which fills this point, and then it comes up to the 0, comma, break. And then 2, comma, minus 2, 2, comma, minus 2, right? And this right here should come all the way up to the break, because you have to have a certain continuity in your graph even though these represent open coordinates or points of discontinuity. And then we have 3, comma, break, which is right over here, then 4, comma, 1 right here, and 5, comma, 1, but it comes up to this. So everything should be able to connect even by means of these dotted lines. But this right here is a graph of your derivative for this function, and it should be right. So we end our video with this, and I'm going to elaborate on this just as a means of revising the technique we've learned, but also at the same time looking at a new question. We have a function over here, a clear thing which stands out. It is continuous in all aspects, but is not necessarily differentiable, because from this point right here to this point right over here, we have a vertical line. Therefore, a tangent line drawn to it be a vertical tangent line, and when you have vertical tangent lines, you cannot determine a derivative at that point. Therefore, you won't be able to draw a tangent line at that point. We'll come up with some values, and look over here. The graph pretty much flattens out over here, but it's steep in the middle and it flattens out over here. We can come up with some value, minus 10 over here, minus 5 here, minus 2, 0. We'll come up with the same values here, 2, 5, and 10. Let's draw our table of values. You're always looking from left to right in terms of the graph reading and in terms of your tangent line assessment, the slope of the tangent line. Our x values and the potential slopes of the tangent lines, which are always just reasonable guesses, not usually more than that. Values minus 10, minus 5, you could disagree with these values and say minus 3, minus 4, minus 1, it doesn't matter. But just try to stay consistent with your estimating procedures. And you know, these look symmetric usually, so you can have the same numbers here and the same numbers here. At minus 10, I'm usually going to find myself on this with a tangent line which is upwards. It's going to be a positive slope but not too steep, and I'll just say positive 1. At minus 5, I'm going to find myself here with a tangent line. Again, I'm drawing with the imperfect human hand, so I'll be prone to making these drawing errors. I'll still have a positive slope, but it'll be relatively more steep. I'll give it a positive 2, because 1 is less steep than 2 in terms of slope. At minus 2, I'm right over here, and I have an even more steep, and I'll say it's a positive, but I'll say it's a steep. At 0, I have I could even put a minus 1, because at minus 1 over here, I'll have a very steep slope. We can remember that. At minus 1, and we'll put positive 1. At minus 1, I have a very steep positive slope. Okay, at minus 1 we'll have a very steep, but at 0 we end up on this vertical tangent line, so there's no slope of a tangent line, there's no differentiability over there. At positive 1 I end up being relatively steep over here, and I'll say positive very steep as well. At 2 I'm right over here, now I'm beginning to flatten out. I'll stay consistent with what I have over here. I have a positive but steep. At 5, I'm going to flatten out some more. Hopefully it's not getting too messy, but you can see it. It's still positive. These slopes of tangent lines are still positive. I'll say at a positive 2, and at 10 I'm going to be relatively flat, and I'll say positive 1. You can imagine if you go further out, like minus 20, minus 30, or positive 10, you'll be very close to a zero slope. Now that we have these table of values, let's do our graph of the derivative function. The derivative of the function. Let's come over here. At minus 10, we have a plus 1. So at minus 10, we have a plus 1 right over here. At minus 5, we're relatively coming up. At minus 2, we're shooting up some more. At minus 1, we've shot up quite a bit because it was very steep. Now let's skip this. Let's skip this for right now. Let's come over here. Positive 1, it was very steep. We'll come over. It's going to mirror pretty much these points. At point 2, it was relatively steep. At point 5, we had a positive 2 in terms of the y character. And 10, we had a positive 1. This right over here is going to generate a vertical asymptote, which you see right over here. And your derivative graph would be something which would look like this. I won't go over that writing, but you can see it would come out like this. And that's how your derivative function graph would be. Remember, the derivative in itself is a function. It just happens to be a derivative of a given other function. And you can see over here the graph of the derivative and the graph of the original function. A derived graph from this using a procedure that now shouldn't be too hard. I won't go too much into repetition over here, but you've seen the procedures that have been laid out before you, and it's not very hard. You just have to have reasonable determinations of slopes, of tangent lines, not secant lines, because at each point of your interest, which are your x-axis value estimations, at these points of interest you're coming up with reasonable estimates of what a slope of a tangent line would have been. And using these x and y values, where the y value represents the slope of the tangent line, you come up with your graph, and that ends up being the graph of the derivative. And that's it for this video. I hope you enjoyed it. Hopefully it is educational for you and a relatively new topic for you, and a break from the norm of being less technical versus what we've been doing so far. And I hope you enjoyed it. Thank you for watching. Have a nice day. Bye.